One of the most beautiful things about science is that sometimes you could be studying this one little thing, okay? You're like, hi, one little thing, I'm studying you, right? And you could keep studying it and get to know it better and better, and suddenly you have an epiphany. Oh my God, this one little thing that I'm studying ends up explaining something else that was a complete mystery that I didn't even see the connection between the two. That is beautiful, and these are the moments in science that scientists live for. So this exact same thing happened with electricity and magnetism. We started looking at electricity, and we started looking at magnetism, and we noticed that, well, if I have a changing electric field, right? If I have a charge that's moving, it creates a magnetic field. And then Faraday comes along and is like, well, if I have a changing magnetic field, that creates an electric field, right? An induced voltage. And so now this means that there's this kind of weird dance between these things. If I change an electric field, I have a magnetic field. And if I change that magnetic field, I have an electric field. And so suddenly they're bound together, right? This changing electric field creates this changing magnetic field, right? And vice versa. The magnetic field then goes on and creates the electric field. And so you can't separate the two. And so you have something called electromagnetic radiation, right? And then we took a look at what rate this electromagnetic radiation should travel at, and we found out that the speed of that radiation was the same as the speed of light. Could that be a coincidence? Absolutely not. That's not a coincidence. Things like that are just too perfect and too beautiful, and suddenly we realized that light is actually just electromagnetic radiation, right? And it's, in particular, it's electromagnetic radiation that our eyes happen to be designed to be sensitive to, okay? This was a huge breakthrough. And it also kind of, begged another question. Well, if we're only able to see these certain frequencies of electromagnetic radiation, what happens if you either increase or decrease that frequency, right? Do you get different kind of light that we can't see? And we found out that the answer to that question was also yes. There are radio waves, there are microwaves, there are infrared waves. And if you increase the frequency, there are ultraviolet waves, there are X-rays, there are gamma rays. And we suddenly, like this whole spectrum of the kind of radiation that we can use to transmit information and to communicate with each other, and a million other possible applications, including remote controls and cell phones, become available to us. This was a true scientific revolution, and we will begin exploring that revolution in this chapter. But first, I would like to talk about the quote of the week, which is from a mythologist named Joseph Campbell, and he says, "We must let go of the life we planned so that we can enjoy the life that is waiting for us." Now, I have a gut feeling that this quote really resonates with a lot of students, because when you enter college and you work your butt off, right, you have a vision for the life that you plan, right? And this is just a reminder that it's okay if it's not always exactly what you planned. You can evolve, you can change, you can experiment, you can grow. My personal story with respect to my experimentation with what I wanted to do with my life is far too long for this one video, but if you ever want to ask me that question, I'd be happy to answer it in office hours or in some one-on-one meeting. But it is proof positive that someone can fall into exactly what they're supposed to be doing, even if their original vision was nothing like they planned. All right? And I also wonder if we would freak out a little bit less about grades and feel less compelled to, do whatever it takes to get the grade if we weren't so attached to one specific idea of how life is supposed to unfold. Okay? So think about that. Maybe that there is a life out there waiting for you that's not what you planned, but it's one that you would even enjoy more. Okay, moving on. Why do we care about electromagnetic radiation? There are so many reasons, from sunsets to rainbows to ultraviolet vision to bending of light, which is called refraction. These are all manifestations of electromagnetic waves and more. which we're going to begin exploring in this chapter. The really amazing thing about this chapter is there is no shortage of applications to the biological and life sciences. Electromagnetic waves show up everywhere in this world, as you will see. So I want to begin with a brief summary of what we've learned about magnetic and electric fields so far. Okay, so as I said at the beginning, if an electric field changes, you get a magnetic field. What do I mean by a changing electric field? I just mean like a moving electron. If you have a moving electron, you have a magnetic field. We also learned from Faraday's law that if a magnetic field changes, you get an electric field and a potential, an induced potential, right? That means, if you change a magnetic field, you get an electric field. And if you change an electric field, you get a magnetic field. And if you put these two together, you have light. And in this next picture, you kind of see what it looks like. I'm not even going to draw it because this picture is so perfect. So we'll put it on the screen right here. This shows you what essentially an electromagnetic wave looks like, right? On one axis, you have the electric field oscillating, right? And then that oscillating electric field inspires an oscillating B field, and the two of them travel kind of like this, okay? Right? It's like kind of a really cool rave dance that electric fields and magnetic fields are doing. And I'm slowing it down so you could kind of see what it looks like, but really it is tremendously fast. It is 3 times 10 to the 8 meters per second is the rate at which these oscillating fields propagate through space. That's astonishingly fast, right? How fast is this? Well, it's about 180,000 miles per second, and the Earth is about 25,000 miles around. So that means if I'm at a rock concert and I flick on a lighter over here in San Diego, it'll whip around the planet more than 7 times, right, in 1 second, okay? That's one beam of light, right? And yet, from an astronomical perspective, it's quite slow. Okay, how slow? Well, for example, our nearest star is 4 light years away. Okay, that means that even at this astonishing speed, if I wanted to send a text message, which also moves at the speed of light, because it's still electromagnetic radiation. So if I want to send a text message to our nearest star, Alpha Centauri, right, then it's going to take 4 years for the light to get there and 4 years for the light to come back for a minimum response time of 8 years. Now, that is approximately what my current response time is via text. But, it's still a little bit of a bummer that if we do find aliens over there, it's not going to be easy to have, a flowing conversation. It would be pretty awkward with that kind of wait time. All right. So this might sound like a cheesy rom-com line, but it's actually true. You can see what this dance between electromagnetic waves looks like. In the next video in the module, there'll actually be a little simulation that shows how these waves work and how it propagates. But there's another video here, or another picture here on this next slide, which lets you see it from another angle. And you might be wondering, well, how are these waves actually created? Okay, so in a nutshell, electromagnetic waves are created by electrons moving up and down in a conductor. What is a conductor where electrons are moving up and down? It's just an antenna. That is what an antenna. So when you see like these antennas, all it is a conductor that's able to both have electrons jiggle, so it transmits electromagnetic waves. Because when you have a jiggling electron, right? So just to kind of make this a little bit clearer, if you have an electron on here, right, moving up and down, right, then that's going to be a jiggling electric field, magnetic field that changes, right? Which then also means that you're going to have a magnetic field that moves along with it, right? Obviously, the drawing on here is better. I give up. Anyways, you get the idea, right? So a jiggling electron creates a changing electric field, which creates a changing magnetic field, which means you have electromagnetic radiation. And so antennas have 2 purposes, right? You could either like create the jiggling electron, right? That sends a field, right? But if you also have a field coming in, right? So I have an electromagnetic wave coming in, right? Then this antenna is going to feel this electromagnetic wave, and the electron in there is going to start jiggling, right? And then that jiggling electron will send a current off to the receiver, and we'll be like, oh yeah, that's Miley Cyrus coming in through the antenna, right? So antennas do two things. They can send electromagnetic waves by jiggling electrons, and they can receive electromagnetic waves because the electromagnetic wave will jiggle the electron, and then that will be seen as a current inside a receiver that then gets sent to the speakers and creates the sound that you hear in your cars. Okay? So that's how these waves are generated. Obviously, this is only one way that they're generated. There's many, many other ways. For example, exciting an atom. If you excite an atom and an electron falls from a higher energy level to a lower energy level, you also get electromagnetic radiation in the form of a photon that comes from that situation. Okay, so next slide. All the light that we see are actually waves made of dances of oscillating electric and magnetic fields. And you can see that for the longest time, we only knew of a very specific spectrum called the visible spectrum of this light. And that ranged from about 700 nanometer wavelengths to about 400 nanometer wavelengths, from red to violet, or Roy G. Biv, as many of you know. Okay, so everything you see, from the reflection in the mirror to a sunset, is possible because electromagnetic waves enter your eyes and stimulate the optical parts of your brain. All right, and it just happened to turn out that these specific frequencies are optimal for human survival. Right, these frequencies will tell us, what we're interacting with in the world that could potentially be something that would be nutritious to us, right? Which is why green, which is the color of most plant life on the planet, is actually one of the more sensitive parts of our visual spectrum.